Okay, what if you could actually see heat? Imagine for a second stepping into a completely invisible world, a world where darkness just doesn't exist, and where heat itself becomes visible, acting almost like a superhero sidekick for your eyes. What if you could look at a totally solid wall and spot the wooden beams hidden behind it? Or gaze out into a pitch-black forest and clearly see the glowing outline of an animal? Welcome to The Explainer. Today, we're pulling back the curtain on that hidden thermal world. We are going to dive deep into the fascinating physics and the incredible technology that allows us to unveil the invisible forces radiating all around us every single second of the day. Okay, let's dive right into this. We're going to cover the invisible light spectrum, the physics of heat, the laws of infrared radiation, how thermal cameras actually work, and finally wrap up with cooled versus uncooled detectors. Starting off with Section 1. The invisible light spectrum. We have to start by acknowledging a fundamental limitation of our own biology. The human eye is amazing, but it's really only built to see a tiny, narrow sliver of the vast electromagnetic spectrum. Just beyond the red end of the light we can see exists the infrared spectrum. And the biggest takeaway here is that virtually all matter emits at least a little bit of infrared heat. Unless an object is exactly at absolute zero, that's negative 459.67 degrees Fahrenheit, where atoms literally stop moving, it's going to emit infrared radiation. Seriously, even a freezing cold block of ice is wiggling around at the atomic level, and because of that movement, it gives off heat. And humans have been trying to capture this invisible energy for a long time. Back in 1800, astronomer Sir William Herschel actually discovered infrared just by passing sunlight through a prism and using a thermometer to detect the heat past the visible red light. Fast forward to 1829, Leopoldo Nobili invents the thermocouple to measure these shifts electrically. And then in 1880, Samuel Pierpont Langley invented the bolometer. This instrument was so sensitive it could pick up the heat of a cow from 400 meters away. Pretty wild, right? But to really get what those early scientists were detecting, we need to zoom way, way in. Which brings us to Section 2, the physics of heat. Think about it down at the quantum level. When energy, like heat or electricity, hits an atom, its electrons absorb that energy and jump from their ground state up to an excited level. But they don't want to stay up there. When those electrons eventually relax and drop back down to their ground state, they fire off that excess energy as a particle of invisible light called a photon. Basically, the hotter the object, the more frantic that atomic wiggling becomes, and the more infrared photons it blasts out. Moving right along to Section 3, Laws of Infrared Radiation. Let's ground that atomic physics with some concrete rules of the universe, specifically the math behind black body radiation. First up is the Stefan-Boltzmann law. It sounds complicated, but it basically just dictates exponential growth. If you double the absolute temperature of an object, it doesn't just double the energy, it radiates 16 times more power. To put that in perspective, that's exactly why a 600 Kelvin kitchen oven is just pumping out so much more infrared radiation into your kitchen than the countertops right next to it. Then there's Wien's displacement law. The general rule of thumb here: the hotter the object, the shorter its peak emission wavelength. Room temperature objects emit these nice, long waves in the far infrared spectrum. But as an object gets intensely hot, think of the glowing coils on your electric stove or the surface of the sun. Those wavelengths compress. They get shorter and shorter until they push right out of the infrared spectrum and burst into visible light. That's why intensely hot things start glowing red, then yellow, and eventually white hot. Now, what's really interesting about this slide is the concept of emissivity. Objects at the exact same temperature can give off completely different amounts of heat, based entirely on what they're made of. Human skin, for instance, is highly emissive, sitting at roughly 0.95 to 0.98. It releases heat wonderfully. But look at polished aluminum. Its emissivity is just 0.05. It practically traps its own heat. And because materials with low emissivity, like those polished metals, don't emit their own heat well, they act like thermal mirrors. They bounce the infrared radiation of the environment right off of them. We call these thermal lies. You might be looking at a shiny floor with a puddle of water, and the camera shows what looks like a freezing cold hole in the ground. But really, it's just reflecting the cold ceiling above it. You always have to account for the material you're dealing with to avoid being tricked. All right, Section 4, how thermal cameras work. So how do we actually capture all of this? Well, regular glass actually blocks a ton of infrared light. So the camera lenses have to be made of special materials like germanium or silicon to let the heat pass through. That lens focuses the infrared radiation onto a detector array, which builds a highly detailed temperature pattern known as a thermogram. That raw data is then zipped over to a processing chip, which instantly maps those signals into visual data for the display screen. Here's the really wild part, though. Thermal cameras do not actually take pictures, not in the way your smartphone does. Regular cameras capture reflected light. Thermal cameras, on the other hand, are effectively reading thousands of absolute temperature values simultaneously. Then they use software to paint a color-coded landscape that our eyes can actually understand. Hotter objects get painted with brighter, warmer colors, and cooler objects get assigned darker, cooler shades. And that leads us perfectly into Section 5, cooled versus uncooled detectors. The detector array is really the heart of the camera, and it basically comes in two distinct flavors. On one hand, you have cooled detectors. These are literally sealed inside a cryogenic vacuum. By freezing the sensor to extreme sub-zero temperatures, you eliminate all the internal heat noise. This gives you pinpoint sensitivity, like detecting a difference of just 1/100th of a degree. But as you can imagine, they're super expensive and require a lot of maintenance. On the other hand, you have uncooled detectors. They operate right at room temperature. They're slightly less sensitive, catching differences of about 0.2 degrees, but they are incredibly practical. These uncooled detectors rely on something called microbolometers. Picture a sensor array made up of thousands of microscopic pixels, usually built from materials like vanadium oxide. When infrared hits one of these pixels, its temperature rises just a tiny bit, which instantly changes its electrical resistance. The camera simply measures that microscopic change, and because they completely ditch the heavy cooling equipment, they're affordable, compact, and turn on the second you hit the power button. They are the absolute backbone of everyday thermal imaging. And because they're so practical, this technology has become a total game changer across a bunch of industries. Firefighters use it to literally see through thick smoke and find trapped victims in zero visibility. Engineers sweep it across electrical grids to spot overheating components before the whole system fails. Doctors use it to pinpoint hidden inflammation, and even archaeologists are out there finding buried structures just by detecting tiny thermal shifts in the soil. It really is a profound technological leap. As one of our sources perfectly put it, thermal imaging devices are like a sidekick for our eyesight, making us the superheroes of the electromagnetic spectrum. By combining the fundamental laws of atomic physics with some incredibly clever engineering, we've managed to expand human perception far beyond its natural biological limits. So I'll leave you with this final thought. How might seeing the invisible change your perspective of the world around you? The next time you find yourself standing in a completely dark room, just remember, that space isn't empty at all. It is absolutely buzzing with a vibrant, wiggling infrared energy just waiting to be seen. Thanks for joining me on this explainer, and keep exploring the hidden dynamics of your world.